Okay, let us finish our review. If we look at number 11, it's the integral from 1 to 2 of 8x cubed plus 3x squared dx. We know we're going to find the antiderivative of this and then evaluate it at 2 and 1. Well, first, to take the antiderivative of this, I plot an 8. Antiderivative of x cubed is x to the 4th over 4. Then for this term, I pull out the constant 3, and the antiderivative of x squared is x cubed over 3. So what we really have is 2x to the 4th plus x cubed evaluated at 2 and 1. So you're first going to plug in x is equal to 2 minus, then you're going to plug in x is equal to 1. Notice how very important those big old brackets are. Because if you don't have them, you will screw up your difference at the end. So this to the 4th plus this cubed, this to the 4th plus this cubed, and first you plug in 2, and then you plug in 1. Well, that's going to end up giving you 38 plus 8 minus 2 plus 1. It's going to be 40 minus 3, which is 37. Okay. Now, remember, this was we went from here to here by the fundamental theorem of calculus, part 2, because that was the really helpful tool that we had. 13, the integral from 0 to 1 of 1 minus x squared, x to the ninth dx. So we are going to take the antiderivative of this and evaluate it at 1 and 0. So the antiderivative of 1 is x, because the derivative of x is 1, minus the derivative of x to the ninth is x to the 10th over 10. So now we plug in 1. Right, so first we're going to plug in x equal 1, then x equals 0. So we're going to have stuff minus stuff to the 10th over 10. I think each time it's important to write out those and then clearly plug in your numbers. So I think it should be fairly clear when you do this that this is just going to end up being 0. And over here we're going to have 1 minus 1/10, which is 9/10. All right. And then our last one, number 15, I give myself some space over here. Number 15 is just going to be the integral from 1 to 9 of the square root of u minus 2u squared over u du. And we know that a lot of math and science is about, yes, form. And that means we need to change the form. So change the form before you do anything. Specifically, this is just equal to stuff to the 1/2. And we know that a plus b over c can be rewritten as this over c and this over c and then add together. Same thing works with subtraction. So we're going to write it as this over u and this over u and then subtract. Why is that great? Because that's just, that's u to the first on the bottom. So if you subtract, you get u to the negative 1/2. Here that's u to the first. So you get 2u du. And now we're ready to integrate. So by the fundamental theorem of calculus, this is just, if I add 1, I get to the 1/2 over 1/2, right? But divided by 1/2 is the same as multiplying by 2, minus 2u squared over 2. So I guess I could leave that for a second as over 1/2, just so we're clear. So that's 2u to the 1/2. These cancel out and I get minus u squared evaluated at 9 and 1. So what that's going to give you is a big chunk of stuff minus a big chunk of stuff, where first you plug in x is equal to 9 and then you plug in x is equal to 1. So we're going to have 2 stuff to the 1/2 minus stuff squared. 2 stuff to the 1/2 minus stuff squared. First you plug in 9, and then you plug in 1. So what that's going to give you is what, 6 minus 81 here in this first set of brackets. And over here, this is just going to give you 2 minus 1. So that's going to end up being, what, negative 76? Okay. All right, so those were all from, again, every time what we did is we used the fundamental theorem of calculus to rewrite this as just the antiderivative evaluated at points. We took an integral, and the way we evaluate a definite integral is to rewrite it using the fundamental theorem of calculus. Okay, so that's a key point on those. Now, we're going to again rewrite using the fundamental theorem of calculus here in just a second, but we're going to use part 1. So if you want to find f prime of x for number 45, that's just the derivative of the integral from 0 to x of t squared 1 minus t cubed dt. So we're trying to find the derivative of this whole thing, right? Well, the thing to think about is that this is really just a function of x. So if I take the derivative with respect to x and I'm integrating from 0 to x, really those two just simply undo each other. And you just get back x squared over 1 plus x cubed. Okay. When it becomes different is something like number 47. So now notice we're trying to find the derivative with respect to x of the integral from 0 to x to the 4th cosine of t squared dt. Remember, t is a dummy variable. It's really not important in this case. It's not used. It's just kind of a placeholder. So what we're going to do is, again, this and this kind of undo one another. So what we get is the cosine of stuff squared. What we do is we take this and plug that in here. So we get x to the 4th squared. But then, because this is a function, so note, bound of integration, right? Bound of integration is a function. So notice that. That means you have to do times the derivative of that function out here. So this is going to be cosine of x to the 8th times the derivative of this is 4x cubed. I'm probably going to put that out front, 4x cubed. So this derivative I'm going to put there, just so I don't get confused when I'm taking the cosine of. Now let's look in here. Now the last one, so notice again, how are those two different? If you're taking the derivative with respect to x of an integral from a constant to x, these undo each other nicely, and you just plug in x. If you have the derivative with respect to x, and this is a function, they undo each other with this plugged in, but you also must put the derivative of that function on the outside. So now if we're talking about 49, so how is 49 even more different? It's the integral from root x to x of e to the t over t dt. So how is this different from before? Well, we now have two functions, one on top and one on bottom. So here's what we're going to do. We are going to change the form. So first thing I'm going to do is I'm going to realize that if I take the square root of a number, there's going to be something in between x and the square root. So in my mind, I see this curve, e to the t over t, and maybe it looks like this. And I'm wanting to find the area from the square root of x to x. I want to find all that area. What I'm going to do is just pick some number in between square root of x and x. Let's call it a. And I'm going to use it to break up that integral into two separate pieces. So I'm going to rewrite it as the integral from the square root of x to a of e to the t over t dt plus the next chunk of area, this chunk of area right here, the integral from a to x, the integral from a to x of e to the t over t dt. So I've just taken one large area from the square root of x to x, found a number that lives in between those bounds, and broken up that integral. So there's an a that lives in between them, to the integral from root x to a, and then a to x. Okay, awesome, good job. And so now what we need to do is now I need to take the derivative. So if I want to find the derivative, so if that's my y, so the derivative is going to be just the derivative with respect to x of the first piece plus the derivative with respect to x of the second piece. Because the derivative of a sum is the sum of the derivatives. So it's going to be root x a e to the t over t dt. This is going to be the integral from a to x, e to the t over t dt. And so how do you break those up? Let's see. That ends up being what? So this one is weird because I don't like this bound of integration on the bottom. I wish it was a constant. So I'm going to flip it, and that's actually going to be the derivative of negative a root x e to the t over t dt. I'm going to flip those bounds of integration on the first one, and this one I'm going to leave alone. So now, finally, after all that work changing form, I think I'm ready to go. So the easier one of the two is this one, so I'll do it first. Notice how this x and this x are going to cancel each other out nicely. So I'm going to get e to the x over x when I take the derivative of an integral. And then, oh, sorry, that's over x. And then over here, I'm taking the derivative, but there's a negative out front. I can just pull that negative out, right? Just pull that negative out. It's going to be negative whatever the derivative of this is. Notice this and this cancel each other out pretty nicely so that this square root of x just goes in here. So we're going to get e to the root x over root x, right? But then we have to do times the derivative of that square root. And we know that that's going to be e to the root, if I can write it in terms of halves, that's x to the 1/2 over x to the 1/2. But the derivative of x to the 1/2 is just 1/2 x to the negative 1/2. So it's 1/2 x to the negative 1/2 plus e to the x over x. That follows me. So then if you want to write it nicely, the 2, it's negative. This is ex over this. Yep, hey kid. This times this, because this negative makes it go on the bottom, just becomes x. And then this 2 goes on the bottom here.
Ooh.
Isn't that nice?
Yeah.
E to the x over x. And so if that's all we do, then I think we're done. So great work.
Great work if you copied it.
Great work if you copied it, Eleanor says. Have a great rest of your day, and I'll talk to you soon.